Welcome to the deep dive. Today, we're getting into something pretty nasty in the petrochemical world, ammonium bisulfide corrosion.
Yeah, it's a big one, often called NH4HS corrosion.
If you're working in refining, you already know alkaline sour water is, well, it's trouble. But NH4HS corrosion, that takes it to a whole different level, doesn't it?
It really does. It's highly aggressive.
So our mission today is to kind of pull together the key factors, the chemistry, where it hits hardest, which materials suffer, and the real headaches inspectors face with this damage mechanism.
Basically a shortcut to understanding a major industrial risk.
Exactly. And we should stress, this isn't just like general rusting you see over time.
No, not at all. This is localized, often incredibly high-speed material breakdown. It's driven by very specific chemical conditions, temperatures, and flow.
Often leading to some pretty major failures in critical units because it sneaks up on you.
That's the danger. It's fast and hidden. Structural integrity can be compromised in, literally months sometimes, not decades.
Okay, let's unpack the chemistry then. Before it can chew through steel, this ammonium bisulfide, NH4HS, where does it form?
Well, it's pretty much unavoidable if you've got nitrogen in your feed material.
Which you often do.
Right. So when that feed goes through hydroprocessing reactors or FCC units, cokers, that nitrogen gets converted into ammonia, NH3.
Okay.
And that ammonia then bumps into hydrogen sulfide, H2S, which is, almost always present in these sour streams.
Sure.
They react, and boom, you get ammonium bisulfide, NH4HS.
So it forms in the hot sections, but the real trouble starts later.
Exactly. The problem really kicks off when that hot effluent stream starts to cool down. As the temperature drops specifically into this critical range, let's say 120 to 150 degrees Fahrenheit.
Which is about 50 to 65 C.
Correct. In that window, the NH4HS actually precipitates out of the gas phase. It forms a solid salt deposit.
And that clogs things up. Fouling.
Precisely. Fouling, plugging, unless you're actively using flush water to keep it dissolved and moving.
So is it the solid salt itself that's corrosive then?
That's a really key point.
Yeah.
Actually, no. The dry, solid NH4HS salt deposits aren't inherently corrosive.
Really? Okay.
They only become corrosive when they get wet. When they become hydrated, dissolve in water, then you get these incredibly aggressive corrosive solutions. That distinction is vital.
Got it. So dry salt is a fouling risk, wet salt is a corrosion nightmare.
You got it. And the severity of that corrosion, once it's wet, it depends on a whole mix of factors.
It's never simple, is it?
No. It's controlled by, the NH4HS concentration, obviously, but also the H2S partial pressure, the velocity.
Velocity? You mean like flow rate?
Yeah, specifically what we call wall shear stress. It's about how the fluid drags along the pipe wall, temperature is a factor, pH is critical, and of course the type of metal, the alloy composition.
You mentioned pH is critical. Why is that so important here?
Well, pH is often your first line of defense, controlling the nature of the scale that forms. Engineers try to maintain a certain alkalinity, a specific pH range, to help keep the iron sulfide scale somewhat protective.
Okay, so the scale can actually help sometimes.
It can, yeah. But if you lose control of that pH, if the conditions become too acidic, for instance, that protective quality vanishes and corrosion can just take off.
Right, and you mentioned concentration earlier. Is there a point where things get dramatically worse, a threshold?
Absolutely. There's a key threshold, especially for carbon steel. Generally, if the solution has less than about 2% NH4HS, it's usually considered non-corrosive or only mildly corrosive.
That's good, 2%.
But once you cross that 2% mark, the corrosion severity jumps up sharply. It's not a linear increase.
Like flipping a switch almost.
Sort of, yeah. It's like a hidden tripwire. Below 2%, maybe you're okay. Above it, the game totally changes and the potential corrosion rate skyrockets.
So now we know how it forms, when it gets nasty, when it gets wet and hits that 2% level. Let's talk materials. Who's in the danger zone? Which metals get hit hardest?
Okay, top of the vulnerability list. Definitely carbon steel and your standard low alloy steels. They suffer significant general wall loss, but also that really dangerous localized corrosion.
And any others that are particularly bad?
Oh yes, copper alloys. The sources are crystal clear on this. Things like Admiralty brass, which used to be common in heat exchanger tubes.
Right, older units especially.
Yeah, NH4HS just devastates copper. It corrodes it incredibly rapidly, catastrophically even. It's basically a material you just cannot use in this service. A definite no-go.
Okay, so carbon steel is vulnerable, copper is out. Yeah. What do people upgrade to? What offers more resistance?
You move up the ladder to things like the 300 series stainless steels, duplex stainless steels, various nickel-based alloys, and even titanium.
They sound tougher.
They offer much better resistance. But, and this is important, it's still relative. Their resistance isn't absolute. It still depends heavily on the specific NH4HS concentration, and crucially, that velocity factor we talked about.
It sounds like even with these better materials, it's not a perfect fix. There are trade-offs.
That's exactly right. It's often about choosing the best available option, understanding its limitations. Take titanium, for example.
Okay.
It holds up really well against the NH4HS corrosion itself. But in these sour water environments, titanium runs the risk of hydriting, hydrogen embrittlement.
Meaning it absorbs hydrogen and becomes brittle.
Exactly. It can
Wow.
lose its ductility, which is a serious concern. Or think about duplex stainless steel. Great corrosion resistance generally.
Okay.
But the welds in duplex can be susceptible to something called sulfide stress cracking, or SSC, especially if not heat treated properly.
And SSC, for listeners maybe not familiar with failure mechanisms, what does that mean practically?
It means sudden failure under stress. It's not like the metal slowly thins out. Instead, a crack forms and grows very quickly, leading to a rupture. It's a major risk for high-strength materials in sour service. Very dangerous.
Okay, so even the good materials have these hidden weaknesses. Knowing that, where are engineers actually seeing these failures? Where are the real hot spots in the plant?
The most notorious problems tend to pop up in hydroprocessing units, specifically in the reactor effluent system, right after the reactor, once that stream starts its cooling journey.
Makes sense. That's where the precipitation starts.
Correct. So areas like reactor effluent air cooler header boxes, the inlet and outlet piping to those coolers, and the piping coming off the effluent separators are prime suspects.
And is the damage uniform there?
Rarely. The really severe damage often occurs where the flow gets turbulent or changes direction rapidly. Think about downstream of control valves,
Why there specifically?
because you often get flashing liquid turning rapidly to vapor, which causes extreme turbulence and high velocities right at the pipe wall. This leads to severe erosion corrosion.
Like sandblasting the pipe from the inside.
That's a good analogy. That high wall, shear stress, the force of the fluid, it literally rips away any protective scale or film the metal tries to form, leaving fresh metal exposed to attack.
And this isn't just a hydrocheater problem, right? You see it elsewhere.
Oh, definitely. We see NH4HS corrosion in sour water strippers, SWS units, especially in the overhead system piping, condensers where the ammonia and H2S can get concentrated.
Okay.
Also in M&E unit regenerator overheads, and in delayed coker gas concentration plants. Anywhere you have that combination of ammonia, H2S, and cooling water.
Now, looking at the damage itself, the morphology, you said it's often localized wall loss. That sounds like finding a needle in a haystack for inspectors.
It is. It's arguably one of the toughest inspection challenges out there. You could scan, say, a long stretch of pipe and find it looks perfectly fine, maybe just some general thinning.
Right.
But the real danger is finding that one small area, maybe just inches across, where the corrosion rate is incredibly high, eating through the wall thickness much faster.
And these spots are usually where flow is turbulent, like elbows.
Usually, yes. Elbows, T's, downstream of valves, reducers,
Yeah.
changes in direction or diameter are high risk. But, and this is the real kicker,
Oh.
severe localized NH4HS damage has also been found in straight runs of pipe.
Seriously? How does that happen?
It's thought to be related to complex flow patterns, maybe unstable flow regimes, even in straight sections. It means you can't just rely on inspecting the obvious spots. You have to be much more thorough.
So you can't just look at the geometry and know exactly where to inspect? That's tough.
It makes it incredibly difficult.
Hmm.
And add to that, if you have areas with low velocity where those NH4HS salts do precipitate and settle out.
Like sludge at the bottom of a pipe?
Exactly. If there isn't enough flow or enough water wash to keep them dissolved, they can build up. Then water can get trapped underneath these deposits.
Ah, and that creates a super concentrated corrosive zone right under the deposit.
Precisely. Under deposit corrosion.
Yeah.
Very aggressive, very localized, and hidden from view until it's potentially too late.
This potential for sudden, unseen failure. It really brings us to the idea of accelerants. What factors take this already bad situation and just make it exponentially worse, potentially catastrophic?
Well, we've hit on velocity and turbulence already. That wall shear stress is a huge factor, especially when NH4HS concentrations are high. It drives that erosion-corrosion mechanism.
Okay.
But perhaps the most potent accelerator, something often found in, say, FCC gas plants or coker gas plants, is the presence of cyanides.
Cyanides. How do they play into this?
Cyanides are really bad news here. They significantly ramp up the corrosion severity because they interfere with that protective iron sulfide film we talked about earlier.
The one that tries to form on the steel?
Yeah. Cyanides essentially dissolve or disrupt that protective scale, making it much less effective or even non-existent.
So they strip away the metal's natural defense.
It's like chemical warfare against the material's attempt to protect itself. When that layer is compromised by cyanides, the underlying metal corrodes much, much faster.
Wow. Okay. And then there's the wash water issue we sort of touched on. You inject water to help, but it can also hurt.
That's the paradox, the tightrope walk.
Mm.
Water wash is essential. You have to inject water, usually upstream of where the salts would precipitate, to dilute the NH4HS and flush the salts away before they deposit.
Makes sense.
But, and here's the catch, if that wash water itself isn't properly treated, if it contains dissolved oxygen or even significant amounts of iron,
Which it might pick up somewhere else in the system.
right, that oxygen and iron in the wash water can actually increase the general corrosion rates and contribute to more fouling downstream.
So you're trying to solve one problem, the localized NH4HS attack, but if your solution isn't pure, you could be creating another problem, like more general corrosion or fouling.
Exactly. You have to manage the wash water quality very carefully.
Okay, this is complex.
Mhm.
Knowing the chemistry, the materials trade-offs, the accelerants, what are the main strategies for prevention and mitigation? How do we actually stop this from happening, or at least control it?
Well, it really starts way back at the design phase. Good hydraulic design is critical,
Meaning?
meaning things like ensuring flow is symmetrical and balanced, especially in heat exchangers like air coolers, to avoid creating unexpected local high velocity or stagnant zones.
Avoiding built-in turbulent spots.
Exactly. And designers need to carefully review the expected localized velocities and the calculated NH4HS concentrations, especially if those concentrations are predicted to get high, say approaching 8 weight% or more.
And if the velocity or concentration looks problematic,
Then you have to upgrade the materials. If velocities are expected to be high, maybe above 20 feet per second, that's around 6 meters per second,
okay,
and the NH4HS concentration is significant, carbon steel is just not going to cut it. You have to step up to more resistant alloys. Maybe duplex stainless steel, maybe something like alloy A25.
and for the really nasty surfaces.
For the most severe conditions, like in those SWS overhead condensers where things get really concentrated, you might see engineers specifying very high-grade materials like titanium or even alloy C276, which is a high nickel alloy. Very expensive, but sometimes necessary.
Right. And managing that double-edged sort of water wash, how do you make sure it helps more than it hurts?
Meticulous control and design. First, the water quality itself. It absolutely needs to have very low dissolved oxygen content. Ideally, it should be desaerated water.
Get the oxygen out.
Get the oxygen out. Second, you need to inject enough water, sufficient excess water, to ensure you're well below that saturation point, keeping the salts fully dissolved.
Dilution is key.
Dilution is key. And third, the injection system itself matters. You need properly designed spray nozzles to distribute the water effectively. And the nozzle and the piping right around it need to be made of resistant material so the injection point doesn't just become a new corrosion hotspot due to turbulence.
Makes sense. So prevention is part design, part materials, part careful operation. But damage can still happen. Given how localized and tricky this corrosion is, how do you approach inspection? It can't just be random checks.
Absolutely not. Inspection strategy has to be targeted and informed. First step, you need data. You have to know, or at least have a good estimate of, the NH4HS concentration in the stream. Is it above that 2% threshold? Where are you on that severity curve? You can get this from process simulations, calculations, or ideally actual sampling.
Know your enemy.
Know your enemy, know the conditions. Then your inspection needs to focus laser sharp on those high-risk areas we discussed. Areas of turbulence are prime targets downstream of control valves, elbows, T's, weld protrusions.
And the water wash points.
Critically important. Inspecting around the water injection quills or nozzles is essential. You need to verify the water is actually going where it's supposed to and distributing properly, not just impinging on one spot on the pipe wall.
Okay, focus on the known trouble spots. What tools do inspectors use? Standard thickness checks.
Standard spot ultrasonic thickness, UT checks, are often not enough because the damage is so localized. You might miss the thinnest spot. We need more comprehensive techniques.
Like what?
We rely heavily on NDT, non-destructive testing. For confirming remaining wall thickness over larger areas, automated UT scanning, AUT, or techniques like phased array UT give you much better coverage. Radiographic testing, RT, can also profile remaining wall.
So ways to see the thickness over an area, not just one point.
Correct. And for screening long runs of piping quickly, especially insulated lines, guided wave testing, GWT, is a really valuable tool.
How did that work?
It sends ultrasonic waves down the length of the pipe. Changes in the pipe wall, like significant corrosion, resect the waves back. It won't tell you the exact thickness, but it flags areas of concern that you then follow up on with more detailed methods like AUT or RT. It's a great screening technique.
Finds the potential needles in the haystack.
Exactly. And for exchanger tubes, which are obviously critical and numerous, that's another specialized area.
Right, you can't easily scan the outside of every tube.
No. So we use electromagnetic techniques from the inside. If the tubes are magnetic, like carbon steel or low alloy steel, we might use magnetic flux leakage, MFL, or maybe remote field testing, RFT, or near field testing, NFT.
And for non-magnetic tubes, like stainless or titanium.
Then we typically rely on eddy current testing, ECT, or for very detailed sizing, Iris internal rotating inspection system, which uses an ultrasonic transducer inside the tube. Different tools for different materials and different levels of detail needed.
Wow, quite the toolkit needed.
It has to be, because the consequences of missing this type of damage can be so severe.
So wrapping this up, the big takeaway really seems to be that ammonium bisulfide corrosion is this intricate dance between temperature, flow dynamics, and specific chemicals, ammonia, H2S, and those nasty cyanides.
That's it, precisely. And controlling it boils down to rigorously managing those factors, especially staying below critical concentration thresholds where possible, controlling velocities, and choosing the right materials for the job.
For me, one of the most surprising things is that double-edged sword, the fact that cyanides actively undermine the metal's own protection, and that even the cure, the wash water, can cause problems if you're not careful about oxygen.
Yeah, it really highlights how in these complex industrial processes, every variable interacts, and every solution often brings its own set of challenges you need to manage. Nothing works in isolation.
Absolutely. It's a constant engineering balancing act. Which brings us to our final thought for you, the listener. Building on this discussion about material trade-offs, think about this. What material characteristics, maybe beyond just simple corrosion resistance, become most crucial for engineers when they're designing systems that have to handle high-concentration NH4HS and simultaneously manage the risk of hydrogen damage, like hydriding in an alloy like titanium? What other properties matter most in that specific balancing act?
Somebody to chew on.
Definitely. That's all for this deep dive. We'll see you next time.